Welcome, everyone. Today we are going to explore the principles of applying data-oriented design. This session is a practical guide designed to help you break through the performance plateau often encountered in modern software development. By shifting our focus from abstract objects to understanding the physical memory layout, we can unlock significant improvements in speed and efficiency. This presentation is based on the influential work of Andrew Kelly from the Zig Software Foundation. As illustrated by the relationship between the processor and the memory grid on this slide, we will examine how organizing data to align with hardware architecture can fundamentally transform your application's performance. In professional software engineering, we often observe a phenomenon known as the plateau of good enough code. This journey typically begins with the struggle, a period spanning the first few years where you are actively learning languages such as Python, C++, and JavaScript. During this time, you often look back at your old code and recognize it as garbage, a vital indicator that you are still learning and evolving. Eventually, many developers hit the plateau. Between years 2 and 15, your progress may stall as you reach a medium level of proficiency. You find yourself looking at code from a year ago and concluding that you would write it the same way today. To move past this stage and achieve the breakthrough, it is necessary to stop focusing solely on high-level logic and start optimizing for the hardware. By adopting data-oriented design, you can push past the plateau of mediocrity and achieve truly optimized high-performance code quality. To understand performance optimization, we must embrace a fundamental mental model. The bottleneck is memory, not math. Modern processors are incredibly efficient at computation, but they are frequently stalled while waiting for data. At the top of our hierarchy, we have CPU registers. Math performed directly on registers is faster than even the L1 cache. As we move down into the L1, L2, and L3 caches, we enter what is known as the danger zone for eviction. If our data access patterns are inefficient, we risk forcing critical data out of these fast storage tiers. The most significant performance drop occurs when we reach main RAM. This is the true bottleneck of the system, operating at an order of magnitude slower than the cache layers above it. Our ultimate goal is to never evict a 64-byte cache line unnecessarily. By structuring our algorithms to do more work on the CPU and less movement through memory, we maintain high throughput and avoid the massive latency penalties associated with main memory access. Understanding the physical layout of data in memory is vital for performance optimization. While a struct containing a Boolean and a 32-bit integer represents 5 bytes of actual data, its footprint in RAM is often much larger. This is due to the fundamental rule of alignment. Structs align their members to the size of the largest element. In this example, the U32 integer requires a 4-byte boundary. Because the Boolean occupies byte 0, the system cannot place the integer at byte 1. Instead, it must skip ahead to byte 4 to maintain alignment. This creates 3 bytes of padding, wasted space that serves no functional purpose. The consequence of this layout is that a 5-byte payload ends up consuming 8 bytes of memory. This results in 37% of your memory bandwidth being wasted on air, which can lead to significant inefficiencies in cache utilization and overall system throughput. Strategy 1 focuses on replacing 64-bit pointers with 32-bit handles to optimize our memory footprint. On a standard 64-bit architecture, each pointer occupies 8 bytes of memory. As shown on the left, a set of 4 pointers consumes a total of 32 bytes. By transitioning to indexes, we utilize 32-bit integers instead. This immediately halves the required space, reducing the total to 16 bytes, and achieving a 50. Strategy 2 focuses on storing Booleans out of band to ensure we do not load dead data into the cache during processing. In a standard object-oriented layout, active and inactive entities are often interleaved. This creates a bottleneck because the CPU must load the entire object into the cache simply to check an is-alive flag. When an entity is dead, that cache space and bandwidth are effectively wasted. By shifting to a data-oriented layout, we separate our entities into distinct arrays, such as alive monsters and dead monsters. This allows the CPU to iterate exclusively over the active dataset, ensuring 0 cache misses on dead entities. The outcome of this approach is a reduced structure size and significantly improved branch prediction, which optimizes overall system performance. Strategy 3 focuses on implementing a struct of arrays, or SOA, approach to eliminate internal padding between elements. In a traditional array of structs, which is often inefficient, each object might contain an 8-byte pointer followed by a 1-byte enum. Due to memory alignment requirements, a 7-byte padding gap is inserted after the enum so that the next object's pointer begins on an 8-byte boundary. This results in nearly half of the allocated memory being wasted as empty space. By transitioning to a struct of arrays model, we decouple these fields into separate contiguous blocks. All pointers are stored together in one array, and all enums are stored in another. This arrangement results in 0 padding bytes because each element within an individual array is naturally aligned with its neighbors. The real-world impact of this optimization is significant. In this example, the memory footprint for 10,000 monster objects is reduced from 160 kilobytes to just 91 kilobytes. Beyond the space savings, this structure also improves performance by increasing cache locality when the CPU needs to iterate over a single specific field. Strategy 4 focuses on managing sparse data in hash maps. The core principle here is to avoid making every object pay for a use case that only occurs 10% of the time. On the left, we have the main struct. This should be reserved for high-frequency data, fields like HP and position that are utilized more than 50% of the time. By keeping this struct lean, we ensure that the most commonly accessed data remains compact and cache-friendly. For data that is rarely needed, we use a technique called offloading. Instead of including an item held field in every single monster struct, we move that data into the exception cloud, a hash map where the key is the monster indexed and the value is the item. This way, we only perform a lookup when it is strictly necessary. To see the impact of this, consider a scenario where only 10% of monsters hold an item. By removing that field from the main struct and storing it as an exception in a map, we can reduce the memory footprint of 10,000 entities from 366 kilobytes down to just 198 kilobytes. This strategy significantly optimizes resource allocation by ensuring that memory is only spent where it is actually being used.
Strategy 5 introduces a powerful optimization we call the super move, replacing virtual classes with tagged unions. In standard OOP polymorphism, objects are typically allocated a uniform memory block based on the largest class in the hierarchy. As shown on the left, even a small B object is forced into a 32-byte footprint to match the larger classes. This means smaller objects are essentially paying a tax for the memory requirements of larger ones, leading to significant wasted space. By shifting to tagged unions, the data is shaped by what it actually is. Instead of a one-size-fits-all container, a human occupies 13 bytes, while a bee only requires 1 byte. This technique of grouping data by type-specific tags allows us to reduce the average object size from 32 bytes to just 17 bytes. This reduction in footprint optimizes memory density and improves overall cache efficiency. To see how these rules apply in a real-world production pipeline, let's examine a case study of the Zig compiler. The diagram outlines the standard progression from source code to machine code, passing through tokenization, parsing, analysis, and code generation. Our primary focus is the highlighted section, covering the intermediate data structures created during tokenization, parsing, and analysis. In this target area, we maintain complete control over the memory layout. By carefully managing how these structures are represented in memory, we can significantly optimize performance and minimize resource overhead throughout the entire compilation process.
Optimization 1 focuses on the token itself through the aggressive stripping of redundant data. Historically, our old token structure was quite heavy, weighing in at 64 bytes. It carried a wealth of information for every single token, including line and column numbers, end positions, string literals, and enum types. To reduce this footprint, we applied 3 key strategies. First, we introduced laziness. Line and column numbers are no longer stored up front. Instead, they are calculated only if an error occurs. Second, we use inference, where the end position of a token is inferred directly from its type. Finally, we utilize deferral, postponing the parsing of string literals until they are actually needed. The result is our new token, which has been condensed down to just 5 bytes. By storing only a tag and an index, we have achieved a massive reduction in memory overhead while maintaining all necessary functionality.
Moving on to optimization 2, we focused on refining the AST node by applying encoding strategies to our tree structures. Originally, each node was implemented as a union with padding, which resulted in a bulky 120 bytes per node. By optimizing the encoding, we reduced that average size to just 15.6 bytes. As the diagram illustrates, we transition to a structure of arrays approach, where nodes are stored in contiguous memory and linked by 32-bit indexes rather than traditional pointers. This change significantly improves cache locality and reduces memory pressure. The benchmark results are clear. This memory layout shift alone yielded a 22% improvement in wall clock time. This slide illustrates the cumulative results of our optimization strategies, highlighting both the significant performance gains and the benefits of what we call the embarrassingly parallel bonus. First, we achieved a substantial 39% reduction in total wall clock time, which represents a major leap in overall processing speed. This improvement is further reflected in our throughput metrics, where the system now processes an impressive 8.9 million lines of code per second. The core driver of these results is our implementation of parallelism through a structure of arrays, or SOA. By organizing data into a contiguous array format, we enable lock-free multi-threading across our thread pool. This architectural choice eliminates the overhead of traditional locking mechanisms, allowing multiple threads to work simultaneously without contention. This design not only maximizes hardware efficiency, but ensures that our throughput scales effectively with the available processing power.
To optimize for performance through data-oriented design, we follow 6 fundamental rules. First, we must identify bloat by finding the specific structs with the highest count in RAM, as these offer the greatest potential for improvement. Second, we prefer indexes over pointers. Replacing 64-bit pointers with 32-bit integers reduces memory overhead and improves cache density. Third, we split booleans out of structs and store them in separate bit sets or arrays to prevent wasting bytes on alignment and to allow for efficient batch processing. Fourth, we eliminate padding by converting data from an array of structs to a struct of arrays, which ensures that similar data types are stored contiguously in memory. Fifth, we embrace sparsity. If a field is empty more than 50% of the time, we move it into a hash map to keep the primary data structure compact. Finally, we use encodings, favoring tagged unions over base classes to avoid the overhead of virtual function tables. By consistently applying these techniques, you will achieve significantly faster code.